Oh, hi everyone. You caught me drinking my coffee. In this lecture, we are going to be taking a look at the solar system. We're kind of taking a move away from all of our conversations about energy, and we're going to move into some Earth space science and take a look at the solar system. So let's first take a look at this first image. Now, this is an image that was taken from one of our space telescopes, and as you take a look at this, there are more stars here than you could even begin to count. And most of the images, most of the dots that you see here are not just stars, they're actually galaxies, which means that there are trillions of stars. So we're going to focus on our solar system. Now, if we take a look at this image of the solar system, this does have the 8 planets of our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Notice there is no Pluto. Pluto is a dwarf planet. When we first discovered Pluto, we thought that it was the only one out there, and so we gave it its own name, yada, yada, yada. But as we learned that it's not the only one like that out there, we had to demote it to a dwarf planet. Nothing about that changed. It just happens to be the way that we see things. There until we name all of them out there, then we don't need to just name one. We thought it was the only one out there, then sure. And its orbit was never in the same plane with the rest of the planets anyway, so it seemed kind of odd. This particular image has all of the planets shown as equal size, but rest assured they are not. They are absolutely not the same size relative to each other. But we do have the 4 inner planets: Mercury, Venus, Earth, and Mars. Those are the 4 rocky inner planets. And then Jupiter, Saturn, Uranus, and Neptune, which are the 4 gas giants out of on the outer edge of our solar system. Our solar system is roughly 5 billion years old. Give or take. It's between 4.5 and 5 billion years old. Now compare that to the age of the universe, which is between 13 and 15 billion years, depending on the calculations that are used. What happened before that is an irrelevant question, because there's no way that we could ever collect data and try to make an observation of anything that came before that. So that question is kind of an irrelevant question. It's nothing that we can answer scientifically. But we do know, based on the age of the items that are in our solar system and the how we can calculate the age of the sun and whatnot, that our sun and solar system is roughly 5 billion years old. Here's an image showing the planets and their relative sizes. And as you can see, we have the 4. Now, this is absolutely not in relative distances from each other in our solar system, but they are in the correct order away from the sun and in their relative sizes. And this obviously is a composite image where you have the 4 inner planets: Mercury, Venus, Earth, and Mars. And then the 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. And this does show Pluto out here, even though we're kind of going to disregard that at this moment. So let's begin with the beginning. It's such a good place to start. So the Big Bang Theory. What exactly does the Big Bang Theory say? The universe evolved from an explosive beginning. Now, don't think about this as an explosion like dynamite exploding or something like that. This is matter expanding from a central point. That's what Big Bang actually is. That all matter in the universe was located together in a dense state, and as it began to expand, that's what we call the Big Bang. And that expansion continues today, which is why if we were to look at everything in the universe that we can see and run it backwards, we see everything coming back together into a central spot, into a very dense spot, so that all the matter would have been like one spot. That's what the Big Bang is. So supporting evidence that we have for the Big Bang, the fact that the universe came into existence as an expansion point, is one, we do see the universe itself expanding. Okay, we've talked about Doppler effect when it comes to sound. Well, we also use the Doppler effect when it comes to looking at the light from stars, and I mentioned that when we were talking about the Doppler effect of sound, because of the fact that the light from pretty much everything that we see is redshifted, which means that it's moving away from us. Well, if everything's moving away, that means that the universe itself is expanding. So as things expand, the light coming from stars is shifted into the red area, the longer wavelengths, because we're getting fewer crests, fewer wave heights hitting us at one time. And so we see that as a red shift, a shift towards the red end of the spectrum. So that tells us they're moving away. We also see a constant background radiation that is pretty flat across the entire visible universe that we see. And it's at about 4 Kelvin, which is awfully cold. That's only 4 degrees higher, 4 kelvins higher than absolute zero. But it's pretty consistent. It's pretty flat across all of the visible universe, and that's this background radiation of 4 Kelvin. Plus the relative abundances of elements. We can measure the abundance of things like hydrogen and helium and so on in the universe. And so as a result, by thinking of the way that elements are fused together to make other elements, we can calculate the fact that the universe is in that neighborhood of about 13 to 15 billion years. And also the relative abundances of those particular elements gives us an idea of the fact that the universe is continuing to not only expand, but it gives us an idea that it started all together, giving us this big bang. So what's going to be at the end? Well, who knows? Depending on how much matter there is in the universe itself, we could reach a point where gravitational pull pulls things back together and we end up with a big crunch, or things could continue to expand forever and the total amount of energy could simply diminish as things move farther and farther away. And so that's that continues to be a subject of debate. And then we get into things like dark matter. How much dark matter is there in the universe, and will it hold the universe together? And those are conversations for astronomers and cosmologists. But nevertheless, I do want you to know that those conversations are going on. So what do we see when we look in the night sky? The night sky has been looked at ever since there were people. People have been looking at the night sky, and in ancient civilizations, it was a whole lot easier to see things in the night sky because there wasn't so much light pollution. When you look up in the night sky, you do see stars. Stars do generate their own light. We know this because that big star that's the closest thing to us, the sun, is generating its own light by nuclear fusion. And so stars generate their own light. We see them twinkling because of our own atmosphere. As their light comes through our atmosphere, it's refracted. And we've talked about what that means, as even light, as it moves from one medium to another, it's going from the vacuum of space through the atmosphere, causes refraction. So we see this as twinkling, light as stars twinkling. And we can measure the distance to other stars in light years. So what is a light year? A light year is how far light will travel in a year. And light travels awfully fast, about 186,000 miles per second. And so it's an awfully fast moving substance, light. And the distance that light moves in 1 year is referred to as a light year. Our planets are visible to us, not because they generate their own light, but because they reflect light. And when we talked about light, we talked about the fact that things will either reflect light, they'll absorb light, and that sort. So planets reflect light. So most of the planets we can see in our night sky, we see because of the fact that they are reflecting light. Typically, you can see Venus in our night sky. Sometimes you can see Jupiter, Saturn. Sometimes there are oftentimes that you could see Venus, Mars, Jupiter, and Saturn all in the same night sky. But when those alignments occur, you can see them, but they're visible because of the fact that they're reflecting light from our sun. So what is a star? A star itself is a massive, dense ball of gas. Because of the fact that it's so massive, remember when we talked about gravity, gravitational pull, wonderful Newton's laws? All of this mass is pulling in. And as that mass pulls in, it starts to heat up. And as it heats up more and more in the core of this star, it starts a fusion reaction, nuclear fusion. And because of that nuclear furnace, it starts to push outward. And then the light, the energy that is being released from nuclear fusion in the center of the star may take millions of years to actually get to the surface of the star, depending on how massive the star is. So once it gets to the surface of the star, then the star starts to be visible and give off visible light. And that's what we see. So nuclear fusion, which was ultimately caused by gravity, generates, it releases the energy according to E is equal to mc squared. Every time you have a fusion reaction, some of the mass is converted directly into energy. And ultimately that is the energy that is released in the form of light and heat, and all the way across the electromagnetic spectrum when stars are operating. Our star, our sun, we call it Sol, S-O-L, is an average star. Okay, it's a yellow star. It's average size. It's about the average age of a star of its type. There's really nothing special about it other than the fact that it's ours. And when I say ours, I mean the entire solar system. Stars form from gaseous nebula. Okay, and typically if you were to see nebula, which is a big cloud of gas out in space, we refer to that as a nursery for stars, because any kind of gravitational wave or any kind of disturbance that starts this big ball of gas moving, you could end up getting it condensing into what's called a protostar, where it's a big ball of gas. So gas nebulae, which are mostly hydrogen, if they get disturbed, they will start to move, and as they start to move, those particles will come closer together, and the gravitational pull will pull them together, and eventually you get a ball, a big sphere, and that sphere starts to condense on itself, and that ignites the nuclear furnace, and you start to release heat energy and light energy, and so there you have a star. When we start to take a look at stars, we look at something called the Hertzsprung-Russell diagram. So the Hertzsprung-Russell diagram is a diagram that compares all of the stars. So if we start to plot these, it's a lot like a scatter plot, if you're familiar with scatter plots and statistics, where we compare the temperature of a star. We compare the temperature of a star to how bright it is. The temperature of the star to how bright it is. So if you notice on this, we're getting brighter as we go up, and it's getting cooler as we go down this way. So that stars here are very bright and very hot. Stars up here are very bright, but they're not all that hot. Stars down here are not very bright and not very hot. And then stars in this area are not very bright but very hot. And so we can see that we have the white dwarf stars. These are relatively hot, but they're not that bright because they're very small. Betelgeuse, which is one of the largest stars that we can see in our sky, is a red supergiant, and it is both hot, it's very cool because it's a red star, but it's extremely bright because it's so large. Here's our sun right here. We're right on this main sequence. Okay, our sun is a main sequence star. There's really nothing outside the ordinary about our star. It's right in the middle of being average. So if we think about the life of a star, Okay, when a protostar, you have a protostar where the gravity pulls all this gas together and it will ignite the nuclear furnace. So it will start to glow and it will it's producing this light as it releases heat energy and light energy. So it will continue to do this and it will reach an equilibrium point where the pressure pushing outward as a result of the heat and light that is being produced matches or equals the gravity pulling it down. So this keeps pressure on it. So the nuclear furnace continues to run and continues to fuse molecules together. But then the energy that's being released is continuing to push outward, and so we get this balance. And so when a star is in its prime life, it has this balance, this equilibrium of gravity pulling down and pressure pushing out. Depending on how much fuel it has, it will do one of several things as it starts to run out of fuel. If it's something really, really massive, then it may have a really high core and surface temperatures, but it's going to use up its hydrogen really rapidly. And if it's less massive, then it may have lower temperatures and it's going to take longer to use up its fuel. So here's an image showing this equilibrium of outward force and downward force. Once a star reaches a point where it may be beginning to run out of fuel, it will expand. Okay, so it will start to expand, and as it expands, the surface will cool, and so you end up with what's called a red giant. And as it expands and continues to cool, there's not as much gravitational push on it, and so you don't have as much. You're using up all of your fuel, and so then you have less and less push going outward. If the outer edges of the star have already reached a certain point, then the star actually may just kind of dissipate. Otherwise, it may start to collapse on itself depending on how massive the star itself is. So if you have fewer hydrogen fusion reactions, there's less energy. Less energy means that you have less outward push. So what happens is the star starts to collapse. And if it is less massive, then the helium fuel is used up. Hydrogen is fused into helium. Helium is fused into lithium, and so on and so forth, and you move up the periodic table up to the point where you get iron. Once iron starts to be fused together, then it's causing more energy to actually fuse them together than is being released, and so that's a point where the star actually will start to collapse on itself, and then you end up with a core. If it is, depending on how massive it is, if it collapses on itself, it may very well blow up or literally fly apart when it collapses on itself due to the gravity, in which case you have a supernova. You could actually have what's called a nova, where you end up with a core that is not really producing any heat anymore, but it hasn't collapsed on itself yet, and so you could get a production of hydrogen on the outside, and then it just all of a sudden ignites, and then you have a bright star for a few minutes, and then it goes back down, and so that's just a nova, and so you have that possibility too. Depending on how massive the star is, that's going to determine whether it ends its life as a dwarf star or if it ends life as a supernova, because it all depends. For really, and this is what I was saying, really, really massive stars, when you end up contracting the carbon, when you start to get carbon fusion and then ultimately iron, all of that energy, all of the fuel is used up, and it collapses on itself and then results in a massive explosion, and that's referred to as a supernova. And what's left at the end of a supernova is just a really tiny core of the star. If you have it even more massive, okay, if the core is more than 3 solar masses at that point, then it starts to collapse on itself, even to the point that it essentially it collapses beyond the physical universe, you might say, and it becomes so dense that not even light can escape. And when that happens, what you have is referred to as a black hole. And so here is a bit of a diagram showing you, here's our nebula, the protostar, a main sequence star. If we have really high mass, then we could end up with a supernova, which could either end up being a neutron star or a black hole if it's really, really massive. If it's a mid-mass star, it could become a red giant and then a planetary nebula and then ultimately a white dwarf, because that's just the core of the star that's left. If it's low mass, then once it becomes a white dwarf, it could end up being what's referred to as a brown dwarf. It's the core of a star that is no longer even producing heat or anything like that, and it's just a cold core of the star. Large scale structures. Okay, you may have stars are often found in binary systems. It's actually far more often that stars are in binary systems than they are in planetary systems. You might have clusters of stars that are come together or that are formed together, and so you have tens to hundreds of thousands of stars that are all packed together, and they share that common origin in that large gas nebula. Or you could have galaxies. Galaxies are collections of billions of stars that are bound together gravitationally. We live in the Milky Way galaxy, which contains, billions of stars. Even beyond that, we have clusters of galaxies and then superclusters of galaxies. There are just billions and billions of galaxies in our universe. The size of our universe is beyond comprehension for most people. It's difficult to even think about how large our universe actually is. So our galaxy, the Milky Way galaxy, we can see the stars of our galaxy. Depending on where you are, you might be able to see it as a band of stars. And what you're doing when you see that band of stars across the night sky, what you're actually looking at is you're looking straight across the arm of our galaxy. So it's visible as a diffuse band on a dark night. Billions of stars. We have a small group of up to 1,000 stars that are bound together. We have a galactic nucleus. There is evidence that there's a large black hole at the center of our galaxy. That's kind of the gravitational pull of that black hole is what is maintaining our galaxy. It is a rotating galactic disk that has a diameter of about 100,000 light years. Well, put that in perspective. What that means is that our galaxy alone is so large that the light coming from one side of the galaxy would take 100,000 years to get to the other side of the galaxy. We have a halo of smaller clusters that surround our galaxy that are called globular clusters, and they're kind of symmetric, almost spherical clusters of stars that are kind of like a halo around our galaxy itself. So here's an image of the galactic arm. So if we're looking out and we can see the galactic arm, this is what it looks like from Earth, obviously. So if we looked at a diagram, then we would see the center of our galaxy. Here, like I said, there's evidence supporting the idea that there's a black hole here. And then these arms that are formed by gravitational waves surrounding the center of our galaxy. And then we have this halo of globular clusters that surround the galaxy itself, outside the arms. And our sun is about 3/4 of the way out on one of the arms. 3/4 of the way out of one of the arms of the galaxy itself. It is a spiral galaxy. So, origins of our solar system. This is referred to as the protoplanet nebular model, or the nebular model of solar system formation. So, we've already talked about the way that a star forms. Well, it's the same idea for the formation of a solar system. We have a nebula, which is a large gas cloud, and sitting there. If it's once it's disturbed, it will start to spin. As this starts to spin, because remember that whole inertia thing, once an unequal force acts on something, it will continue unless an unbalanced force acts on it. That's Newton's first law. So we end up with this nebula that is slowly spinning. Well, as things to spin, then you end up with a condensation towards the center. As heavier matter starts to move towards the center, or the matter itself starts to move towards the center, then you get a cloud in the center that starts to form a big gas ball that ultimately is the sun, and this also is forming a disk. So you have the sun in the middle, or the protostar in the center, with what is referred to as an accretion disk. Well, the accretion disk is just a disk of material that is, because of gravity, is revolving around this protostar. And as rocky material, gaseous material starts to also aggregate in this accretion disk, that's when we get that's where we get our planets from. The heavier rocky material is pulled inward towards the sun, and that's why we end up with our 4 rocky planets to the center. The lighter materials move outward, and that's why we get the 4 gas giants that are out there: Jupiter, Saturn, Uranus, and Neptune. And so this is the way that our solar system forms. Once our sun, the proto-sun, becomes a star, it literally blows away. It literally blows away a lot of the lighter material, and that's why that all ends up moving out towards the outer solar system. And also is why typically only heavier materials are left closer to the center of our solar system. So as things cool, then we end up with planetary cores, and we end up with planets. So here's kind of a diagram of that happening. Here's the protostar with an accretion disk. Things start to solidify, and you end up with a star and planets. And one of the reasons that we know that this is what has happened is because we can actually see this happen. The universe is running this experiment for us. We can look across the galaxy and actually see this happening in various places and at various stages. So it's not like we just kind of made this up. We can see that this is happening, and this is the way that planets form around stars. So our solar system has our sun, so 1 star, 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then over 100 moons. We have over 100 moons scattered out across our planets, and then thousands and thousands of asteroids and small icy bodies and comets and whatnot like that in our solar system. The distance that we refer to, sometimes we're talking about an astronomical unit. Because we are on Earth, we tend to use the distance between the sun and our own planet as a standard distance. So 1 astronomical unit is the average distance between the Earth and the sun, and so that's about 1.5 times 10 to the 8th kilometers. So 1.5 times 10 to the 8th kilometers is an astronomical unit, or an AU. So we use this AU as a way to measure the distance to other things, as just a way of comparison. So we need to compare the size of our planets, the density, and their atmospheres. The terrestrial planets, the rocky planets, Mercury, Venus, Earth, and Mars, these are mostly rocky materials, nickel, iron. And then the gas giants, Jupiter, Saturn, Uranus, and Neptune, are mostly hydrogen, helium, and methane. So you've got these huge balls of gas. In fact, Jupiter, if Jupiter were much more massive, then Jupiter probably would have been a second star, which probably would have been bad for the rest of us, because if Jupiter had been a second star and we did have a binary system here, then in all likelihood the other planets would not have formed. We took a look at all of the matter in our solar system. Over 99% of that matter is in the sun. Of all the matter that's left and that is not the sun, roughly 99% of that is in the planet Jupiter. All the rest of it makes up the rest of the planets. And Pluto, which is only one of many dwarf planets, it orbits way out to the end. It is not nearly spherical, and it's not really in the same plane of orbit that all of the rest of the planets are. So it clearly formed in some other way, which is also why we don't really consider it a planet anymore. It's outside of what we refer to as the ecliptic. It doesn't orbit in the same. It's not in the same plane with the rest of the planets. Planets orbit the sun because of inertia. Remember we talked about the moon orbiting the earth because of inertia. All the planets would move in a straight line if it weren't for gravity pulling them forward, and so literally all of the planets are falling around the sun. So the gravity keeps them close. They want to move forward, and so they end up orbiting or falling around the sun. We have looked at the orbit, the order, a couple of times with Mercury, Venus, Earth, Mars, then Jupiter, Saturn, Uranus, and Neptune, and there is an asteroid belt between Mars and Jupiter. Chances are it could have formed another planet, or there may have been another planet there and it got destroyed, and so we end up with the asteroid belt because when it got destroyed, and then so you end up with all of the asteroids simply or all of the parts of the planet that was there forming a ring around the sun. In all likelihood, that's how Saturn also has rings. Saturn has rings, and chances are that's because it had several moons that broke apart, and so they ended up forming rings around Saturn. We also know that, Jupiter and Uranus also have rings as well. All right, so let's walk through each of the planets. Mercury, it's very hot. It's the innermost planet, closest to the sun. It has no atmosphere. It's also the smallest, and it has a highly elliptical orbit. What that means is, well, none of the orbits of our planets are round. They're not circular. They are all elliptical, which means that they're in the form of ellipse. Because in parts of their orbit they're closer to the sun, and parts of their orbit they're further away from the sun. So it's not a complete, it's not a circle. It's actually an ellipse around one of the two foci, and the sun is at one focus of the ellipse. Sometimes Mercury can be seen shortly after sunset or before sunrise. It's highly cratered because, well, what direction is everything going to be moving in our solar system? Towards the sun. So if there are asteroids or meteors in our solar system, they're going to become flying towards the inner solar system, towards the sun. And so Mercury is highly cratered because it's constantly being hit with objects who are in our solar system. Mercury has no moon. Here's an image of Mercury. Venus. Typically Venus appears near sunrise or sunset, and actually often beyond that as well. Typically it can be some of the brightest things in the sky after the moon and the sun, of course. We see Venus in phases like the moon, and that has to do with the way that the sun is reflecting on it and where we are in relation to the light that is being reflected. Venus is strange in that it rotates in the opposite direction from any of the other planets. Think about the Earth, the way that the Earth rotates. We observe what appears to be the sun rising in the east and setting in the west. Now, even though the sun isn't going anywhere, but as the Earth rotates, we see the sun come up in the east and go down in the west? Well, Venus rotates in the opposite direction, which means that on Venus, if you could stand on Venus and watch the sunrise and sunset, sun would rise in the west and set in the east. Another thing that's really strange is that it takes Venus rotates so slowly on its axis. It literally takes longer for it to rotate on its axis than it does to make one full revolution around the sun. So a year on Venus is shorter than a day on Venus, which is very strange. Yeah, don't think about that too much. You might hurt yourself. We have sent probes to Venus, but because the atmosphere itself is primarily acid. I mean, literally, it rains sulfuric acid on Venus, and the temperature